Okay, guys, this is chapter 6 and the beginning of our study in vectors and introduction to vectors. And we're also going to do, in the next 2 weeks, touch on chapter 7, some applications with vectors. Very, very straightforward vectors. A lot of you guys have been introduced to vectors through science and physics classes. If you're lucky, maybe a little bit of talk in some math class application questions. Velocity style questions are very common with vectors, and you see a lot of it in physics too. And we're going to touch on just some of the basic principles of vectors um, and some applications, and then hopefully we'll get into chapter 8 and chapter 9 here, where we talk about vector lines and planes and 3 space. Okay, so vectors is a vector quantity is the concept of understanding that we've got both magnitude and direction with vectors. Scalars are what you're used to working with in math and some other physics and science applications, where it's simply just a magnitude. And there's early in this chapter, okay, here's our intro, okay, and then here we're going to learn in chapter 6, talking about vectors as line segments, okay, where they have both magnitude and direction, some mathematical operations, some properties, and then introduce you to algebraic vectors. So we're going to be successful when we do sort of all these things and work through these. Okay, so what's the difference between a scalar and a vector? Well, a scalar is a quantity that's just represented by a number and a measurement unit. So for some common examples here, okay, are age, okay, in years, or volume, okay, in terms of cubic centimeters, let's say, area, speed, mass, temperature are all common scalar applications that you've seen. Vector quantities are magnitude, not only magnitude, but also direction. Okay, so some examples here are weight. Common examples would be weight, velocity, friction, okay, and force. With geometric vectors, we can talk about geometry, so lines, right? We have geometric vectors, just some common terms here. We can represent a directed line segment with the notation, okay, AB here, like this. Okay, so as my directed line segment starts at A and goes to B, okay, I can have the arrow, okay, and then the letters here. And geometrically, that looks like sort of this by way of a vector statement or directed line statement. And that's when we talk about geometric vectors. We refer to A as the initial point or the tail of the vector, and B is the final point or the resulting point or the head of the vector. Algebraic vectors, we use the Cartesian plane. Okay, so we can talk about coordinate system vectors, and you guys are used to, okay, coordinate system and Cartesian plane where x and y, and we might very well have a vector A where it would be 1, 3, let's say, where I'd go 1 unit in the x direction, okay, and I'd go 3 units in the y direction. A lot of work in algebraic vectors introduces a third coordinate, okay, and we'll see that coming up. We'll see that all throughout this section here, where not only have we got x and y, but we've got a z coordinate system or a z plane, and that's depth, right? And since we're talking about vectors and more common applications, when we talk about depth, like a volume of a shape here, we've got length, bandwidth, and height, right? Or okay, or to the left or to the right, up or down, or okay, deep depth here, so backwards. Okay, and that's how we'd have that. And if we had a vector with representation of a 2, 3, -1, we talk about 2 units to the right, 3 units up, and 1 unit backwards. Okay, our position vector. We often have a thing called a position vector, where it starts at the origin and goes to a particular point. And that's the notation for position vectors generally includes O for the origin. Okay. Okay, or that would be O in 3 coordinate system here. Okay, 0, 0, 0. A displacement vector, we can talk about AB, again, this directed line segment. So we're moving from A to B. The magnitude of a vector, how I calculate the magnitude of the vector? Well, I use the Pythagorean theorem, since a lot of vectors make, okay, 2-dimensional triangles or 3-dimensional triangles. Okay, we can use Okay, the Pythagorean theorem to come up with the calculation of a magnitude. So let's do a couple here. Let's do an easy one. We'll go back to our original vector. Let's go 3, 1 here. Maybe that wasn't our original one. So the magnitude is represented like this, and I use the Pythagorean theorem, and I calculate the first component squared and the second component squared. So this particular example would be, what's that, 9 plus 1 is 10, so the root of 10. So the magnitude of my vector A, where A is the vector 3, 1, the magnitude is represented with bars, absolute value bars, root 10. In this particular example, this would be the notation, and I could really quickly so I've got, what's that, 4 and 9 and 1, so square root 14. Magnitude's an actually a pretty easy calculation to do, and you don't need to show a lot of steps for magnitude. It's a very common thing. Make sure you've got magnitude down here. Notice that it's direction, right? Magnitude is the distance traveled between or along the three components. So that's why we square it and take the square root. So the -1 is irrelevant in the magnitude calculation, because I square it, becomes positive, and then I add them all together and take the square root. So if I travel a distance of -1, the 1 is the distance I travel. The negative number represents the actual direction, and magnitude is only just simply direction. Okay, so let's see about this one here. AG. Okay, here's a diagram, and it looks like, okay, rectangular parallelepiped, or cuboid is the following relation is true. Okay, I don't think there's a proof here. It's not asking me to prove, but notice that the vector AG, okay, when I square it, I can find it as, okay, or the direction, okay, of the three components. So that would be A, okay, then to B, then to C. Okay, so that would be the same as going all the way from A to G directly, or traveling A to B to C, and I do the squared if I actually wanted. This is actually a magnitude, right? This is a magnitude question, okay, as evidenced by the bars and the squared symbol. Okay, let's take a look at some of these other ones. I'm just going to take a second and get to make exactly sure what I'm asked to find here. Calculate the magnitude of the following. Okay, so A, B, okay, I've got our regular hexagon. Okay, A, B, C, D, E, F all the way around, and each side length is 2. So I'm just going to label, okay, and represent that they're all the same. Okay, so I want the vector AB. Well, AB, that's pretty straightforward. Okay, how about AC? AC would be this vector here. Okay, so I'd use some trigonometry to find the length of that. Okay, I'm going to pause this and do that calculation here in a second, but it looks like, okay, I need to find my interior angle there, and I think if I have that calculation, I don't have my calculator with me, okay, but the interior angle that would be needed, then I'd need a cosine law, okay, in order to get that. AD, okay, would be a little bit, okay, a little bit more challenging. That would be this, okay, length here as well too, okay, and I need, okay, that, okay, extra side of a trapezoid here. So I'm going to save those calculations for a minute, okay, and pause this and, okay, get back to you in a second. Okay, the hardest part, I had to pause this. I hadn't done this yet, and I hadn't really taken a look at it, so I wanted to avoid you guys watching me work through this. And I realized the hardest part was calculating these interior angles. Okay, so back to, I'm just going to try and do this relatively straightforward. Back to grade 9 math, I can take this hexagon and cut it into 4 triangles, right? Each triangle has 180 degrees, okay, and there's 4 of them, okay, so I get, okay, a calculation here, okay, where the total interior angles are 4 times 180. Now, then, Okay, I've got to divide them by 6 because not only, sorry, I've got to divide them by 1, 2, 3, 4, 5, 6. Yeah, divide it by 6. Okay, because they're this in the interior angles, there's 6 of them. Okay, and they're all equal. So I think this calculation is 120. Okay, so what that means is each interior angle is 120. Okay, so there's a 120 over here, there's a 120 over here, there's a 120 over here, and a 120 here, and a 120 here. Now I wrote this above it and this one above it just because those are two vectors. But what I mean is this is the 120 in here. So AC, okay, is found using the cosine law, and the calculation for that would be, I'm going to square this for now, okay, and that's going to be 2 squared plus 2 squared, that's the two arms of my triangle, then minus 2 the other two sides times the cosine of the interior, okay, embedded triangle here. So as I work through that, I get 4 plus 4 plus 4, or 12, and that's still a squared. So basically my AC vector is the square root of 12, or 2 root 3. Okay, and that makes some sense, I think, if you understand that it's obviously it's going to be longer than 2, so that's a factor of 2, and then there's a square root 3 idea in it. Okay, now the next one, AD, is a little bit more challenging with respect to the angle, but it turns out that it's actually pretty easy. So here's AD, this one, and it's made up of two sides. I've got two sides that I've already calculated. The 2 root 3, that was AC from above, and then I've got this side 2 of my triangle. Now I need to figure out this interior triangle here. This one was 120, and it's an isosceles triangle, so that means I'm left with 60 left over to share between two equal angles, so that would be 30 and 30. That leaves me with a 30 in this area right here. I know the whole thing was 120, right, from my previous calculation. If I know part of it's 30, that means that the remaining is 90. So really I've got to calculate this AD side, and it's a right triangle, and I know my sides are 2 root 3, 90 and 2. I'm going to zoom right ahead and go to I'm making a disaster of this. I'm going to zoom ahead here, and try and draw this a little more properly. So see, I've got AD, and my diagram looks like this. This is A, this is C, this is D. I'm going to calculate this vector. I know that's 2, I know this is 2 root 3, and I know that's 90 degrees, from some previous calculations. Well, I don't need, I don't need cosine law or sine law in this case. I just need a straight, Pythagorean theorem. So I'm just going to adjust this a little bit. So that would be, so 2 root 3 squared, that's 2 squared is 4, and then 3, and then 4, so I've got 16, and that was our 4, and that distance is 4, so that AD is 4, and I hope that diagram explains it a little bit better. Okay, let me shoot back to the rest of this. My apologies for the mess here, not anticipating that I should have had that one done. Equivalent vectors. We can say vectors are equivalent if they have both the same magnitude and the same direction. So just by observation, these two vectors, AB and CD, are equal, and I say that using this notation. That's a very very straightforward, but make sure that you have both size or magnitude. Okay, magnitude is often referred to as the size of the vector, okay, or the length of the vector, and the direction have to be the same. Sometimes you might have to measure them and prove that. Opposite vectors. Vectors can be said to be opposite or going in when they go in the opposite direction, but they have the same magnitude. Okay, in this particular case, okay, I write this statement here. By observation, it clearly looks like they're going in an opposite direction, and that's the only criteria for vectors to be opposite if the direction is the reverse. Okay, so the magnitude has to be the same. Okay, that's represented with the straight bars. Okay, but I can say something like that. Now that's a little bit different here. Okay, DC. I could, in relation to, okay, vectors, like if I said AB is equal to CD, it's something I can say, okay, but I'm reorienting the vector here. So I'm suggesting that it starts at C and goes to D, and these would be equal vectors, but I've reversed it, and I can talk about these being opposite. Here's my equality statement. Okay, I have to go DC and then put a negative sign on it. So the vector DC is going from D to C, but putting the negative sign on it reverses it again. Okay, so 3 pair of equivalent vectors in the diagram. There's a whole pile of, okay, this is a cube. I'm going to assume it's a cube. There's a whole pile of answers here. I could say AE is equal to DH. I could say AE is equal to CG. I could say AE is equal to BF. Okay, I could say all kinds of them here. Now I could also say, okay, I think that satisfies CG. Now remember, I have to go in the right direction. Okay, not only, okay, I could have used EF as my start vector and went all the way across. EF would have been equal to HG, would have been equal to AB, it would have been equal to DC, or I could have used, okay, EH. If I wanted to start, I could have said EH is equal to FG. I've seen students do diagonals, so AH is equal to BG. Okay, there's all kinds of pile of answers here. How about 3 pairs of opposite vectors? Okay, 3 pairs of opposite vectors. Okay, I'll do this. I'll answer this question properly here. 3 pairs of opposite vectors. Okay, so I'm going to go AE. Okay, and okay, G, C. So what I've done there, I've gone A to E, but I've gone G to C. Okay, and that's opposite. So we just erase that. I don't want to mess this up again. Okay, give me another set of opposite vectors. How about EH and GF? Okay, let's go off the board here. Let's go BG and so BG is opposite HA. Okay, state a pathway from A to G using a combination of vectors. At least 5 edges. Okay, we want to go AG. AG, so we gotta go diagonal across. Okay, let's start at A. Let's start AG, and I'm gonna say, okay, you have to start at A. So we're gonna go A, let's say E. Okay, now I'm at E, so let's go E to F. Okay, now I'm at F. Let's go F to H. Now I'm at H. Okay, let's go down to D. So H, D. I got 5. I got 4. Okay, now I'm at D. I can go D, C. And let's finish this little trip. I'm at C, and let's go to G. So C, G. That's it. I've got 5 edges. 1, 2, 3, 4, 5, 6. Okay. It's like going out, driving in a car on a Sunday, right? Let's take a drive to Ottawa. Well, let's go through Prescott. Let's go through Spencerville. Let's go Spencerville to Kemptville. Okay, and let's go to Kemptville and go across to Winchester and then end up in Ottawa. Okay, all these different little side trips here. Okay, that we could go directly from A to G if we wanted to, or we could go a variety of 5 different edges, they're called, with vectors. Okay, go back to that. Notice though, I continue to say, okay, I'm now at E. Now I start from E. So notice some patterns here. AG, vector AG, starts at A and ends at G. Okay, I hope we see that. Okay, so no matter how I do this, I have to start at A and end at G, and my connecting points will have to match here, right? Okay, I think you notice that and make probably a lot of common sense in that, but that's an easy way to sort of make sure you've done this properly here. Okay, finally direction. Okay, how do we represent direction? Sometimes we can represent direction, okay, with a reference system, okay, and consider it algebraically. So we talk about our true bearing. So our north, okay, our vector north is going this way, east, southwest, so like a compass setting. Again, we can also talk about sometimes with a bearing, okay, a bearing. So a bearing includes a degree, and the degree is always north, okay, in a clockwise direction. So we start at 0, okay, and if we're going, okay, 5 meters per second, 120 degrees, that bearing is 120 here, okay, going in that direction, that clockwise direction. Okay, sometimes we talk about quadrant bearings. So again, northeast, southwest quadrant, and I can go north 45 degree east. So I start that off as going north, then 45 degree in the east direction. That's in the east direction. If it was like north 60 degrees west, I'd start at north and then go 60 degrees in the west direction. That would be 60 degrees here. Okay, so that's how we do, okay, quadrant bearings. Okay, and that is it. Okay, I think for the most part these, okay, are pretty easy. A couple of drawings, a couple of just understanding. Okay, understanding. Okay, just some basic principles and ideas of equal vectors or opposite vectors or magnitude. A couple of magnitude calculations. Make sure you understand magnitude and you know how to do magnitude. That comes into play a lot here. I have not included answers to any of these. I think you can figure out the answers to these. If you're at all really stuck and you haven't checked in the back of the textbook, send me an email, no problem with that. Okay, but if you're really stuck with these, okay, I think you probably should be able to figure out the solution by just looking at the answer in the textbook. I did do number 11, and it's included in my homework help page in chapter 6. Okay, that's it. Good luck.